All right. Thanks for coming back. Okay, so far so good. So now the part 2 of my talks, I want to talk about localization at K-theory. Okay, so now we're going to fix a prime P, and for this talk, I'm going to take P to be odd. Okay, so the reason I'm taking P to be odd is for the presentation. I'm sorry, you said 2 was good. I agree, 2 is good. If you know me, you know that usually this is not my favorite place to be. I like to be at the prime 2, but the presentation is easier for the odd primes. There's a story completely analogous to everything I'm going to do at the prime 2. You just have to fiddle a little bit. Okay. All right. So we're going to fix an odd prime, and what's going to be our goal? We'd like to understand. Okay. So I'm not going to go through all the details, but understand, discuss, get used to the localization at of the sphere at these 2 theories. Okay. All right, so on board. So that's sort of what I'm going to talk about. There's going to be a lot of things that we're going to have to take for granted, but that's just my general goal. Okay, so let's talk about. So we're trying to understand localization of this, and let's say, sorry, I think I want the goal to be this. I'm going to change, sorry. Okay. I might fumble a little bit because this morning at 9, I realized I could do this better. So I'm changing the order of what I have in my notes. So you'll have to forgive me if I mess up a tiny bit, okay? So, okay, so we're going to understand localization at this thing. So if I want to understand localization of S at this thing, then it would be good to sort of, well, we're going to need, so what are we going to need? We're going to need a map that is an equivalence. So this is going to have to be a K mod P equivalence. And this guy is going to have to be K mod P local. Okay. So we should try to map the sphere into something that's local for this guy. Okay. And then we're going to hope that we find something where this gives us an equivalence. Okay. Does that make sense with the goal of like what it means to be a localization? It means you have an equivalence to a local guy. Okay. So we don't know what this says, but we're going to look for something and we're going to try to build it in with this philosophy in mind. Okay. All right. So let's see. So and let me just make sure that people know what K is. So okay. So K theory, right? So this classifies complex vector bundles over topological spaces. That's a cohomology theory. So there's a representing spectrum, right? And it's Z cos BU is the 0 space of the spectrum, right? And then U Z cos BU. So that's K theory. That's all I mean. I just mean good old complex K theory. Okay. So what's the homotopy? What's the K theory of a point? Maybe I could do the K theory of a point. Well, that's going to be the integers in degree 0 adjoint some gadget. And actually, let me do it in homology, where U is going to be in K2 is the bot class. Okay, so maybe that looks different, but let's see. From what you're used to, so what do you know about K theory, right? It's bot periodic, right? Bot periodicity. So the K theory of a point is Z, right? Because, you know, up to isomorphism, what are bundles over a point? They're just, you know, it's just the dimension, and then we group complete, so we get Z, okay? So what does it mean to take K1 of a point? That's the K theory, that's going to be the K theory of S1, okay? The K theory of S1 is going to be 0, okay? And then what's going to be K2 of a point, that's going to be like the K theory of S2, right? But dot periodicity tells us what the vector bundles on S2 are, right? Up to the group completion, right? So the K theory of S2 is the same as the K theory of a point. That's the big theorem, okay? So then I'm just going to repeat myself, okay? So K theory, K0 is Z, so that's the unit. K1 is 0, that means this guy is in degree 2, so there's no homogeneous elements in this ring of degree 2, okay? And so on and so forth, okay? So that's my K theory spectrum. Okay, so, and when I mean mod PK theory, I take this thing and I mod out by P, so mod PK theory is going to have these coefficients. Okay, so we're localizing at this homology theory, and I think that's all I'm going to have time to say about it. Okay, so let's see. So we're looking for a map to something that's KP local. Let's go back to that. At the very end, I spent some time telling you how if I took P complete E, that was local for the mod P theory, right? Okay, so therefore, let's just start with P complete K theory. That is local for specific to that. Okay, it's a ring spectrum, so there's a map. Okay, and okay, so we could ask, well, is this an equivalence? Okay, but okay, so what are the homotopy groups of P complete K theory? I just have to add a P here. Okay, I just take the p-adic as my integers. So let's see, we can ask, okay, so is this going to be a K mod P equivalence? So that's going to ask us, well, we'd have to take like the K mod P theory of this thing. So that's going to be what we have over there. And then we'd have to take the mod PK theory of P complete K theory. Okay, now this thing is not going to be the same as K theory. So let's just do that. So let's do KP star of this thing of S, and then we're going to do KP star of this thing. Yeah.
So another way to weakly interpret the goal is that we want to know what part of the homotopy is detected by K theory.
So K theory doesn't, so detected by K theory as in the image of the Hurwitz, not much, right? But maybe we can do better. So maybe image of Hurwitz is not nice enough. How about if we do like some kind of spectral sequence based on this? Oh, or the image of J. Yeah, so that's going to be the answer. Is going to be like we're going to end up detecting the image of J. Okay. So I'm not going to do like an image in J. It's going to show up, but it's not going to be an image of J-centric presentation because I'm trying to set us up for something else. Okay. Okay. So if I look at this, well, this is going to be FP U plus or minus 1, because that is going to be the same F pi star of K tensored S mod P tensored S, which is going to be pi star of K mod P, and I put it over there. Okay. However, this thing is not this. This thing is huge. Okay. So this thing looks more like something like this. Okay. So this is going to be continuous maps from the group of p-adic integers into this ring. Okay, so and maybe, right, okay, so I'm just looking at, so I take the p-adic integers and I take the units in the p-adic integers, and then I just look at continuous functions from this, sorry, this is discrete, so no, I do need to, that's not. So I'm looking at continuous function into this gadget, okay? So, okay, this seems like it's coming out of the blue, but what is this p-adic thing is that, so here's what is this thing here? This is actually the Adams operations. Okay, so I should not write it there, I should write it below because I'm going to want to finish my sequence. Okay, so here's, oh, I'm not supposed to write over here. I'm sorry. Y'all can call me out if I do that. Okay, so here's a fact. And this is in Adam's Blue Book. I don't know if it's in the book. So if you have some element that's a unit in R, so R is a ring. It's just a commutative ring from algebra, okay? Then KR admits a stable Adams operation. Okay, so this is K theory with coefficients in R. Okay, so as long as I have that the integer Adams operations, right? I have one for each integer. As long as the integer is invertible in my coefficients, then Adams operations don't start like they're not stable. Okay, that's the whole point of the Adams operation. But if the thing is invertible, then actually I can upgrade my thing to a stable map and I get a stable Adam operations. Okay, so in particular, so for each, so this has this P-complete K theory. So that receives a map from the K theory with P-complete coefficients. Okay, so I mean these are the same thing, right? This is the ZP is that this is the p-adic. So so as long as I have a unit in the p-adics, then there's a map, and it's actually a ring map. Now, in the sense of stable homotopy from K theory, P-complete K theory to itself. Okay, so this is a generalization of the Adams operation, and I'll tell you how it acts on the bot class. So if I take my bot class over here, how will it act? Well, my bot class, the coefficients here are the p-adics, and therefore I can, and this is a p-adic unit, and therefore I can multiply with it. So I just multiply my bot class by that. Okay, and in fact, because of some choices I've made, I need an inverse here. Okay, but don't worry about that. So now this should remind you of the way that the Adams operations are, you know, how they interact with suspending with the sphere. Okay, but that's your P-complete Adam operation. Yeah.
It's more complicated than it looks.
It's more complicated than it looks. He told me I'm a terrible speaker before we started the talk. because he said, he said that I'm gonna make you feel like you understand. Okay. All right. Well, I can't, if I'm gonna get to chromatic homotopy theory, I can't not try to make it look easier than it is. Otherwise, we'll all be thoroughly lost, me included. Okay, so I get an operation like this for every integer. In fact, if I look at the automorphisms of the P-complete K theory as an E infinity ring, this is isomorphic to these Adams operations. Okay, so let's see. Maybe a lot of stuff happened that I know from answering questions. I know the background is quite varied, but let's say this guy, some E from before, it's a ring, it's a really structured ring, it's a really nice ring, okay? So ring automorphisms, that's something we know from algebra. You can talk about it in topology as well, okay? So I'm just telling you the automorphism of this ring is the p-adic integers, and it's the unit in the p-adic integers, okay? So that's what that is, okay? So now we're gonna choose some R in the, you can actually choose an integer for this in Z, such that R modulo P squared generates the units in here, okay? Then R, so let's do an example. So if R, so in general, oh no, actually, I'm not gonna do an example. So then CR actually topologic, so then R, I can think of it as a p-adic unit, because if it generates the unit, it's a unit, so that means that p-adically it's a unit as well, and this is a topological generator. Okay, what does that mean? This group looks like a free group on one element, okay? But I have a topology, so I have to take some closure, okay? So I just take the group generated by R. It's going to be some subgroup of ZP cross isomorphic to the integers, because it's just going to be some free copy of Z, and I just take the closure, and then I'm going to get that, okay? So as a topological group, this thing looks a lot like just the integers. Okay, under multiplication, it's like it's not addition, but just looks like a copy of the integers. Okay, so then, okay, so now we start here and we're like, okay, we look at this map, we land here. This is just way too much stuff, okay, way too big. But what if, so now we have the maps from ZP cross into here. What if we tried to take the fixed points instead? Okay, so if I tried to take the fixed points with respect to the ZP cross action, okay, so I have a ZP cross action on this on this group, and I take the fixed points, then I'm going to cut down quite a bit, and I might get the answer I wanted. Okay, so now how do I take the fixed points for a group action? Well, so now R is going to act on K theory, right, by the atom operation. So how do I take the fixed points? Let's just think about it in, like, how would it work in algebra? So what does it mean for A to be fixed? It means that if I act on A by C to the R, minus I do nothing, so this is my identity on C to the R, I get 0. Okay, that's what it means to be fixed for R. But now I have a group that's generated by one element, right? So if I'm fixed for my generator, I'm fixed for everyone. So I just need to make sure implement this relation, okay? And furthermore, the group is free. So there's just like really not anything I have to worry about in terms of like higher derived functors, okay? So I just have to implement this equation, and I can do it topologically, because now what did I tell you? What did I say? I just said, I want this map. So what do I want? The fixed points are the kernel. In algebra would be the kernel of this map, and then in stable homotopy, I can do this by taking fibers, okay? So then we're going to write this, okay? So now we had our map to K, to P-complete K theory, okay? So it mapped here. Now let's see, we're going to call the fiber of this JP. So this is going to be like the kernel of that map, okay? And so now we want to know, does S, we had a map, right, going into here, does it factor through here? Well, let's think. What's happening? These are ring maps, right? Well, how do ring maps act on the unit? They just send the unit to themselves, right? So that's 0. Okay, so I'm mixing algebra and spectra here, but in a way that's allowed, you know, that you can make rigorous. So that means that if I do this, this is null. Okay, so therefore I get a factorization here. Okay, so now let's see. This is K mod P local. This is K mod P local. This is a triangle where 2 out of 3 things are K mod P local. So therefore, this guy is local, okay? GP is K mod P local, okay? And so I have a map now from the sphere to a local spectrum, okay? So I'm parts of the way. It's better than the one I started with, okay? So just because of the fact that it factored, right? So remember, localization is like the initial map to a local thing, right? So if that's local and then I factor my map from the sphere, I had a map to a local thing and it factors through another local thing, this couldn't have been the localization. Now this is the best guess, okay? So now we're like, okay, is this the localization? And the theorem is that this is the K mod P localization. Okay, so let me write that down. theorem, let's see, is that so S the spectrum. Okay, this spectrum, this is called the J spectrum. Yeah.
You need the Agnès conjecture for that, or it doesn't need the Agnès conjecture?
So this is not easy. I'm gonna give a sketch of the proof, and it's gonna use the telescope conjecture. So I think the answer is yes. Yeah. I made it. I kind of brushed over here. So okay. I kind of brushed my hands a little bit here. You know, this is what I do, right, Tony? But this is hard, and I'm going to talk more about it. Yeah. Okay. So at least that's how I understood. That's what I understood that you needed. Okay. So let's see. When am I going to say that? Now I'm going to say that. Okay. So we'd like to know that this is so. Okay. So we want to show. Let's call this eta. Remember, the prime's not 2, so nobody can get confused. Okay, eta is localization. Okay, so we want to show that if I take k mod p tensored with s, and then k mod p tensored with jp, I want to show that this is an isomer. Okay. Because JP is local, that would be done. That's all we need, okay? So we found a map to a local one. As long as I have an equivalence, I'm good. Okay, so now let's open this box a little bit. This is K tensored S mod P tensored with S, K tensored S mod P tensored with JP, right? Okay. But now these I can bring together. Okay, so eta a k mod p iso, this is equivalent to this map. So let's just call it. So this is equivalent to the map from S mod p to S mod p tensor this J spectrum being a K equivalence, being an isomorphism on K theory. Okay, so let's take a second. What did I do? We have our map to our K local thing. We want to our K mod P local thing. We want it to be a K mod P isomorphism. So we want that when I tensor with K mod P, I get an isomorphism. But K mod P is this thing. I can split it up, okay? And I can shove the S mod P on the other side, okay? So remember, S is the unit for the tensor product, so I get S mod P over here. Okay, so now, but now I have a map, right? This inner bit. So I have the map from this bit to that bit, which I wrote here, okay? And I want this map to be an isomorphism, but that's the same as this map is an isomorphism after tensoring with K, okay? So I want that this map is an isomorphism in K theory, okay? So that's an equivalent thing. So we can focus on showing that this map is an isomorphism on K theory, okay? Okay, so the new goal, which I'm not going to give all the details for this proof for sure. That's a very, very computational proof. KP is a K equivalence. That's what we need. Okay. Yeah.
Why should we be led to believe that that's an easier problem than the original one?
I didn't say that. It's equivalent. I mean, I didn't do much, right? So it's not like I changed the problem that much, right? Okay. So I want to talk about this one. Yeah, okay, I want to phrase it that way. I mean, that's how the proof is presented in these papers anyway. So, but I mean, and this is a general trick, you know, that we'll talk about a little bit more later. This is not an unusual move for working in local theories like these ones. Okay, so now we have this thing, the sphere mod p, and now we get to some classical stuff. So now I'm gonna lay down the ideas for the proof. I can't even say that what I'm gonna do is gonna be a sketch of proof, but I'm just gonna lay down the structure of what the proof of this argument looks like. So the first thing we need is a theorem of atoms, and it's about these guys. Okay, so there's a K equivalence. So you have to suspend the sphere this many times to S mod P. And in modern languages, we call this V1. You know, this is often in literature as Adams A map. So it's a capital A. That's what it's known as. Okay. So what is this? So it's a map from the sphere mod P to itself, and it induces an isomorphism on K theory. K theory. Okay, so this is in Adams' J of X4 paper. Where he constructs these maps. Okay, and these are very beloved to homotopy theorists. So like, what is it that we do with this map? I mean, let's see. I have this map here. It starts over there. I'm going to move the suspension to the other side with a minus, okay? Over there, okay? So I just desuspended the map. I'm still going to call it V1, okay? Whenever I move a map around, I'm not going to change the name. Okay, so this is V1. But now think about doing V1 on the inside. Okay, so all I did was do V1 on the inside, so I'll get twice that. Okay, I can keep going. Minus 2k p minus 1. Maybe I should put the minus k times 2p minus 1 of S mod p. Let's give this map, let's give this number a name. Let's call it the degree of V1. Okay, so just this whole number, I'm going to call it Fox V1. Okay, it's going to make writing things like this easier. Yeah. It's because there's going to be others, but you know that. Okay, so I can iterate this thing like that. Okay, and you know, if I do it k times, I'm going to think of this as V1 to the k, just this iteration. Okay. Okay, so I get this, and it's an isomorphism on K theory, which means none of these composites are null. Okay, because that's an iso on K theory, that's an iso on K theory, and so on. Okay, and in fact, so the really cool thing is, sorry, I don't need this guy over here. So the sphere mod P, let's see, the sphere mod P is defined by this co-fiber sequence, right? Okay. So, but now this is a triangle, so I get to continue it. So I have a map from the sphere mod P to the suspension of S. Okay. So now I'm going to start with the sphere mod P. Oh yeah, I do want to start. Okay, so the sphere mod P has a map here. Let's call this A and let's call this B. So it has a map A going in. It also has a map, the sphere mod P, to the suspension of S going out. Okay, so I'm going to write it over here. I'm sorry, I'm going to write it below because, so I'm going to have minus KV1, and now I'm going to add 1 of S like this. Okay. So now what did I construct, or what has been constructed? We have a map from the sphere to some desuspension of itself. Okay. So this thing here, this composite, so it's like A composed with V1 to the K composed with B. This is an element in the homotopy group of spheres. And this is an element in degree minus K V1 plus 1 of the sphere. Okay. And this element is called alpha 1. Okay. I guess it's alpha. Yeah, but it's I took a K, so now I don't remember what we call that. If a K was, I think alpha K. This element is alpha K. Okay. And this goes back to Toda. These elements are never 0. Okay. So for any K, they're not 0 and they repeat, right? I have 1 for every K. And this is a periodic family. So this is the first periodic family. Okay. So if you look at a chart of the homotopy groups of spheres, you'll see these elements appearing everywhere. These ones have order P. Okay. So P alpha K is equal to 0. And they're part of a bigger family, which people call the image of J, which Tony brought up earlier. So these are part of the image of J.
Discovered the color purple in chromatic.
That's right. I've got all the colors. I'm going to use them all. Yeah.
Ask where the word chromatic comes from. There's the color purple.
Oh, that's what you're saying. Yeah. Okay. So the chromatic homotopy theory is there's going to be V1 is surjective. There's going to be Vn. There's going to be more periodic families that come from the generalizations that I'll talk about for the rest of the week during the next 2 days. Okay. And so these things are periodic, and the chromatic, Ravenel gave the name chromatic homotopy theory in reference to like the frequencies in the light spectrum, I believe, or was it sound? Yeah.
Well, the stem-by-stem calculation, that is the time mode. And then the Fourier transform is the frequency mode, it's the chromatic picture.
Okay, thank you.
So one is supposed to be easier than the other.
You mean the chromatic picture, yes.
Hence your existence.
Hence my existence. Yeah, just making sure. I don't like to assume that. As you saw earlier, it's good to think in relative terms. Yeah. Okay, so let's see. Now we have our sphere P. Okay, and maybe I'll say that at the end. I'll just say the things about the image of J at the end. Yeah, at the end. Okay, so we have this map. I'm not going to tell you how to construct it or anything like that. This is classical in atoms, so you're going to have to believe me on that one. Okay, but it's central importance. And now, because none of these iterates are trivial, it sort of makes sense to make the following definition. Okay, we're going to define T1. This is going to be V1 inverse of S mod P. Okay, so what does it mean? We saw earlier how to invert things, right? We just take some colimits. Okay, this is just going to be the colimit of S mod P, sigma minus V1, S mod P. I'm going to take that colimit. Okay. Oh, yeah.
Would anybody like to ask a question? You can't be shy if you're trying to learn something. Would anyone like to ask a question? Yeah, there you go. Thank you. Very good.
I might have missed something, but I think for localization, you probably only mentioned localization with back to objects. And if you do that, I assume you're doing localization with morphisms.
So here, all I meant was if I give you an element, right?
Sorry, you're defining it here.
Huh?
Sorry. I think because I thought you can view this as, because it's an element in the homotopy group, you can actually view it as a morphism in spectrum.
Mm-hmm.
And I guess you can also do localization with respect to morphisms to define such a thing, but I guess that's probably not the way.
No, I mean, I think that like the way that I localize at certain homology theories, like the way I localize the sphere or X was by inverting some stuff, and inverting stuff is called localization, right?
Yeah.
In algebra.
Yeah.
So that's why we have like that word generalized to localizing at a homology theory.
Mhm,
Now, when I say localizing here,
mhm.
like, I mean, okay, let me first say the simple answer and then let me give two answers to your thing. When I said right then localization here, all I meant was if I have some element, right, I have some map between these two things, between something and itself, I can iterate it, right? What does it mean to, like, if I think about in algebra, how do I invert something? I take like the colimit of multiplication by it, right? I just, so that's my categorical construction for inverting something, and I can repeat that in spectra always. So then because I can iterate this thing, I'm gonna call the colimit I'm gonna call that inverting V1.
Yeah, I guess because once you do the colimit, on that colimit, you still have this V1 map, and this map will be invertible.
Yeah,
on
and
the
this map
colimit,
will
so
be an
that's-
equivalence now.
Yeah, so this is an explicit construction of the categorical way of thinking of inverting stuff.
Yes.
Okay, thanks.
And well, okay, so now the confusing answer to your question is that this is, so here's a spectrum, right? So I can talk about localization. So maybe this is like an aside, which I will come back, but so I can talk about localization with respect to that. And that is T1. Localizing with respect to this thing in the other way is the same as inverting this map. Okay, so that's maybe like, that's not what I was saying at that moment, but that is also correct. Okay, all right, perfect. Any other questions?
Any other questions? Would anybody other than me like to ask a stupid question? Oh, sorry.
Yeah,
That was good.
why we are saying that that's not equal to 0, the alpha k, that it will never be 0?
That's a good question.
That's not a stupid question.
you get your microphones where it's reverted.
Okay.
I mean, this is a theorem. Of
Okay.
Koga.
Then the stupid question is why p alpha k is
Like,
equal to
you
0?
know, that this is not, that this one is never 0. It's just that this is an isomorphism on K theory.
Okay.
So if I just repeat an isomorphism, it's not going to trivialize itself.
Okay.
And the K theory of these things is not trivial. Okay.
Okay.
So, but that this composite followed by that composite is not 0. I think that's something that you have to prove.
And what about the p alpha k being 0?
Oh, that it's just in this case, it's just that any element in the homotopy of this thing is p torsion. Okay, I'm at out primes. So every element in the homotopy thing, this thing is p torsion. So therefore, it factors through stuff that goes through like things that can only know about p torsion. So that has to be 0.
Okay.
That one's not so bad. At out primes.
Would anybody online like to ask a question? Any questions online? Thanks very much.
Okay, great. Okay, so now I formed this colimit, this telescope, and from the previous lecture, it feels like a good thing to do, right? And okay, so and then let's look. So this is, I'm going to write it as a lemma, but you could prove this with everything I've told you. If I do this to T1, this is a K equivalence. Okay, so this comes from this comes from the fact that all of these maps are isomorphism after I tensor with K. So if I tensor this diagram with K, it becomes just a tower of isomorphisms. So the colimit, so the map from it to the colimit is an isomorphism. Okay, so this is a K equivalence. Great, and so let's remind ourselves we're trying to prove that this is a K equivalence, right? And now we've produced another one. Okay, so let me rewrite that. So our goal is to prove that that's a K equivalence. So we have our map tensored with the J spectrum. We'd like to prove that's a K equivalence. But remember, so localization, so this thing is K mod P local. Okay, and localization is a terminal equivalence. Okay, so that means that if I have any other equivalence, it has to factor I have any other equivalence and a map to a local map, I have to be able to factor it. So I'm going to get a factorization like this. Okay. And now we know that this is a k-iso. Okay. And this is k local, this one is k local. This is a k-iso. And therefore, what are we missing? Okay, so I'm telling you that this one's k local. I'm brushing my hands a little bit. Okay, so it's k mod p local, but it's also k local. So just trust me on that one. Okay, so now all we would need then is that this is an equivalence. So if this is an equivalence, then that means that this one is k local, which means that because this is a k-iso, that this is a localization. Okay, so we need that this is an equivalence. Let me say that again. So if this is an equivalence, this makes this k local, and therefore we'll have an equivalence, a k-isomorphism from S mod p to a k local thing, to a k local thing, and that will have to be localization, and our goal will be achieved. Okay, so that's okay. And now what is that statement? Let's see. Let's call this. I'm not talking about any S-cyclization, so let me call this. I want to call it theta. Let's call it beta. I feel like let's use. So did I have theorem? Theorem B is that beta. And this is a theorem. At the prime 2, it would be Mahal. At odd primes, it would be Miller. And it's that beta. JP is an equivalence. Yeah.
To construct beta, you already used the fact that a JP is the localization.
No, I did not.
You used the fact that the map is a terminal equivalence. So yeah.
So we have, I don't think so. So we have some k local thing. So our goal is to show this is a k equivalence. Right now we have a map to some k local thing. Okay. What else do we have? We know that we have a k theory isomorphism here, right? So that means that we have the map from the telescope, from SP to the telescope, that's a k iso. Okay. And then we have a map to some k local guy that we don't know anything about, right? So this is just k local. So maybe like the missing bit is that there's S mod p somewhere in life. There's S mod p, there's this localization. So there's a map from here to here, k mod p localization. And we have two things. This is a k iso. So because this is the terminal k iso, I get a map here. This is k local. So I get that a factorization like that for the top map. Okay. And now what do we want to show? Like we're going to show that this is an equivalence, which is going to mean that that's an equivalence and that's an equivalence. And these were both localization at k mod p. Did that help?
Yeah, I guess my question was how is beta constructed, and you just explained how it's constructed.
Okay, great. Okay, perfect. So this is thanks for the question. Yeah. Yeah, that's good. Any other questions? This is good. This is all good.
When we say need equivalence, are we saying need k equivalence?
No, now just an equivalence.
Just an equivalence.
Now we just want that this is an equivalence. So yeah, we know this is an equivalence. So I say k iso k equivalence. I'm using these interchangeably. We know this is a k equivalence. Okay, and now we need this to be k local. So let's make it equivalent to something that's local. That guy. So that's what we need. So that would give us the locality. Okay. Okay, and now this theorem, this is not an easy theorem. Okay, so this is an instance of something called the telescope conjecture. Okay, and this follows from a lot of computations. And more. Okay, so this I won't give it to you, but I think I hope that I hope that I've convinced you that theorem B implies theorem A. Oh, sorry, yeah. Let me write that one here. I hope I've convinced you that theorem B implies theorem A. Yeah.
There is a question online. Is the fact that J sub P is K local just a formal consequence of being KP local and unraveling definitions, or is this something that requires real work?
No, it doesn't require a ton of work. JP is like the P completion. JP is easily constructed as the P completion of something that's K local. So it's just an inverse limit of K local things.
Does that answer your question online? Bryce, is it?
Okay.
Yes.
Yeah. Maybe I can say it quick. Maybe I'll say it at the end if I have time. Stuff is a summon. I don't know the answer to that question. So okay, let me orient myself. Okay, so this is all I'll say about that, but I want to sort of recast this a little bit. Okay, so I've got. So now that we have the theorem, so this is going to feel a little bit roundabout, okay, a little bit circular, but I just want to sort of make a statement from this. So now that we have the theorem, so now with the comment that you got out of me from this, so from the conversation, we have S mod P, we can T1 localize it, and we're going to get this telescope. Okay, so that's written over there. Let me not rewrite it. And now what do we know? We said, well, this is a K equivalence. Now, it turns out that if you're working with S mod P, this is one of the bits that I'm kind of pushing under the rug. If you're working with S mod P, if you're a K equivalence, then you're a K mod P equivalence. And it's because S mod P is already P complete, okay? So over here, this term, this is actually this thing. Sorry. K mod P. Okay, so this is the KP localization, K mod P localization of S mod P, and we constructed a map that wasn't hard, and then there was a theorem that this was an equivalence, right? Okay. Now, okay, so this one doesn't have a 1 associated to it, so let me make another definition. Okay, so we had the K mod P spectrum, okay, and we have an action of the atoms operation. So for any unit in Z mod P, we're going to have an atom operation. Okay, so we're going to have atoms operation for all R. So let me call it A. For any A unit. Okay, and so I can take the fixed points with respect to that action. Okay, so now taking fixed points in this case also isn't something that's difficult to do homotopically because the order of this group is co-prime to P. Okay, it turns out that taking fixed point is just, you can think of it as taking fixed points. And then we get a spectrum, which I'm going to call K1. Okay. And it maps to K mod P. And in fact, K mod P is just the sum of suspension of this thing. 0 to P minus 2 of sigma 2I of this guy. Okay, so now let's look at the homotopy to just get a bit of intuition for this. That was the homotopy of mod PK theory. And now I'm acting, I said that acting on U was just multiplication by the inverse, okay? So if I take CA of U to the P minus 1, I'm going to have A to the 1 minus P times U to the P minus 1, okay? But okay, if I have something in Z mod P, right, and I raise it to the P minus 1, I just get 1, okay? So what is that, like Fermat's, one of Fermat's little theorem or something? Okay, so I get P minus 1. Okay? So this thing is fixed, so it turns out that the homotopy of this thing is just, in homotopy, it literally is taking the fixed points, and pi star of this K1 is just FP of U plus or minus, so let's call it, we're going to call it V1 as well. I know V1 is going to get used and abused in this talk, where V1 is just, we're going to call it this, okay? Just the power, U to the power P minus 1. This P minus 1 is this P minus 1, this V1 is this V1. They all mean the same thing if you kind of allow yourself to have different, the same symbol means slightly different things that are very related, okay? Okay, so now, because this thing is just a wedge of this guy, acyclics for this one are going to be the same as acyclics for this one. So okay, like let's think about it. If I tensor this with X and I get 0, then in this list I'm going to have K1 tensor X, right? So that's going to have to be 0 because I have a sum n that's that, and the sum is 0, so that's going to be 0. So acyclics for this are acyclic for that. And similarly, if tensoring K1 with X gives me 0, if I tensor this side with X, well, I just get a bunch of zeros. Okay, so these have the same localizations. So let me write that. So over here, K mod P, we have a notation for this. These have the same acyclics. This one's just a little smaller. Okay, I've just stripped off some kind of irrelevant, redundant information. Okay, so therefore I can do this. I can change that. Okay, and that this map, now phrased this way, so at height 1 is this statement, and this is very close to what it would look like later. This, like when I generalize it, it'll look a lot like that. Okay? Say that again?
This aspect of the telescope projector is true.
This one is true. The other ones, not true. Okay? But right now we only have that one, so we're gonna. So then at this point, we're Doug and we make a conjecture. Yeah. Yeah.
That's your definition of K of 1. That's a definition of K of 1.
You can define K of 1 that way. Yeah. Okay, so then let's see. I want to say a couple things now to wrap up the K theory topic. Now, these are going to be just some facts that we've sort of alluded to during the talk, but that are going to come back in more general forms. All right, so what do we have? So let's see. We use this, that the E infinity maps of P complete K theory. This was isomorphic to Z mod P cross, the Adams operations. Okay. And I was generated by, we had our generator C to the R. Okay. And then I convince you, well, I don't know if I convince you, but I thought I did, that it's not on the board anymore, but let me write it again. So if I do SK1, right? So this is theorem A here in disguise. So S, let's just remind ourselves what J was, right? J was the fiber this was the definition of J, right? And remember when I introduced this, I said, oh, it's like taking fixed points, right? So SK1 was KP with fixed points, this guy, okay? Let me write it as ZP cross, but the important part is that these are the infinity ring maps of this guy. Okay, and okay. Of course, I've been very loose with my limits. I always mean homotopy limits, homotopy fixed points. For some reason, I have a harder time not putting that H there, even though I've been loose. So okay, so that was theorem A. Okay, something that I sort of used in our motivation, I did not prove it, and I'm not going to prove it, but I used it as that. So like, what do I had? At some point over here, I was taking K mod P star of KP. I don't know if you remember that, okay? So that's like the homotopy groups of this thing, except now with K mod P over there, okay? So now the thing with localizing is that one thing it does not do is preserve smash products, okay? So this is local, doesn't mean the tensor product is local, okay? So then I have to localize, and in fact, this localization is not so hard. This one happens to just be P completion, okay? So all I have to do is P complete this thing, okay? The point is the homotopy groups of K star of this thing inside, it actually like has rational stuff. It's got like huge rational, it's really nasty, and then P completing gets rid of that and only leaves the beautiful part, which is as follows. So this is going to be the continuous map. So now this is going to be, so in some kind of, you have to make sense of what that means, but the p-adics unit, this has a topology. So if I'm looking at functions out of them, I can talk about continuity, and now I get that this is. So this appeared as part of my motivation, right? This equivalence. So here I have an isomorphism, and this one is, and it's an equivalence. This one is correct, okay? And let's say, and then there's one last thing. I don't know if I mentioned this, but I'm going to say it. So if F is a K mod P equivalence, then so if I take KP tensored F, this is also a K mod P equivalence. Okay. So this is the saying that tensoring with KP, this is a conservative functor. That's the statement there. And together these things get packaged as, okay, I've got something, some rings, I've got something, I've got some action, I take some fixed points, I get the fixed points. What does that remind you of in algebra? When do I take fixed points of rings? Say fields, maybe. Fixed points of fields. It's when I do Galois theory, right? Okay, so this is the setup for a generalization of Galois theory. So Agnès set up the name, so for us, but
we're failing the quiz.
You're failing the quiz. That's okay. It's a hard quiz. Okay, so I've got this map here, and it goes to P complete K theory. Okay, so this is the map we started our approximation with. Okay, and then this wasn't the right thing, right? This wasn't localization. We just had to take fixed points to get localization. So there was a kind of like descent. Okay, and what is this? This is a Galois extension. This is a faithful. So the faithful is this condition, pro Galois extension with Galois group. This ZP star, which happens to be the automorphism of this gadget as an E infinity thing. Okay, so this is a Galois extension. Okay, and in some sense, KP is the algebraic closure. I'm not going to make precise sense of that. And it's not really true the way I said it, because I need more roots of unity. I need FP bar to show up somewhere, but of SK. Okay. And this picture, okay, maybe you have a question like, where did that fixed points, you're used to it, right? I have a field, I take fixed points, I get a Galois extension, right? Like the subfield is a fixed point. This is something that should, if you think about it, is the normal basis theorem. But in ring theory, you need to impose the normal basis theorem. Like that's like with fields, you get this for free. When you do Galois theory over rings, you need to ask for it. So this is like the normal basis theorem. Okay. And this picture will generalize quite broadly, okay, to higher localization, to other localizations. So now you knew about K-theory. Well, I kind of came in expecting you to know about K-theory, or if not, just taking me on for granted. But this is something that's like part of what you learn when you read Hatcher, right? But now there are other localizations that are as fundamental as these ones, and that's going to be the goal of the next lecture, is to introduce the other homology theories, the other E's for which we're going to localize. And this picture here is going to generalize. Okay, so that's the goal for tomorrow. Oh wow, I'm over time. Thank you.